everyone. Yesterday I have discussed regarding the deviation of real gas from ideal behavior or deviation of gases from ideal behavior, in which I have discussed regarding the graph of compressibility factor, that is Z, versus what? P. So I got this result that when we are plotting, we are going to plot Z versus P for the ideal gas. It should be like this, straight line with respect to the change in pressure. But when I was plotting the real gases, Z versus P for the real gases, I got like this curve, somewhat positive deviation from this ideal gas behavior, or first negative and then positive. I was getting that. Okay, but now I want to discuss one more graph with PVM versus P and or PVM versus V. Means if we are going to change the volume, there is change in the PVM graph. According to Boyle's law, it should be like this. For the Boyle's law, for a particular temperature of ideal gas, it should be like this. Suppose it is T1 temperature. This is T1 temperature because Boyle's law states that at constant temperature and fixed mass, PVM is equal to constant. So if we are going to change the volume to, there is no change in the PVM value. And at T2 also, for the ideal gas, it is a straight line for ideal gas only. Okay, ideal gas, T3 ideal gas. But when I really plot the graph of the real gas of PVM versus V, I got the graph like this one, and this one. So can you see that I am changing the dip, means the negative deviation here and here? So what is the reason behind that? I am saying that T3 is greater than T2 is greater than T1, means temperature 3 is greater than, suppose it is 500 Kelvin, it is 200 Kelvin, it is 100 Kelvin. Okay, I am changing the temperature to highest one, T3. If I told you that ideal gases remain ideal when it is at higher temperature, because at higher temperature there is kinetic energy of the molecule is very much high, and at low pressure. Okay, so I am changing the temperature because I am assuming that effect of temperature on PVM versus V. On going from 100 Kelvin to 200 Kelvin to 500 Kelvin, I am increasing the temperature. That's why, see, I have at near the lower volume, I have almost graph that is coinciding to ideal gas. For the real gas, the deviation is going to be low and low. When we are changing the graph, we are increasing the temperature. Okay, so this is at T1 temperature, this is at T2 temperature, this is at T3 temperature. Now what is the reason behind, what is the cause of deviation from ideal behavior? Means why it is these gases deviate from ideal gas, cause of deviation of gas. Okay, first is, we consider that in the kinetic gas theory, we consider that volume occupy, cause of deviation of gas is faulty assumption of kinetic gas theory, faulty assumptions of kinetic gas theory. So first is volume occupied by the molecules of gas is almost negligible as compared to the total volume of the gas. And second one is there is no force of attraction. There is no force of attraction between the gas molecules. But this is not true. These 2 points are not true because of these 2 points there is deviation of gas from the ideal behavior. Now, if there is no force of attraction, then Z value remains the same. Means for like the ideal gas, there is no force of attraction. But we are getting, when we plot between Z versus P, we are getting a graph like this, and first negative, then positive. Means there is somewhat positive or negative deviation due to this compressibility factor. If compressibility factor is greater than 1 or if compressibility factor is less than 1, both of this is for the real gases. Means there is some forces of attraction that is holding the molecules together. For Z is greater than 1 means less compressible. Less compressible means attractive forces are less between the molecules. Now, Z is less than 1 means more compressible. Attractive forces are more. So how we can say that there is no force of attraction between the gas molecule? There is some force of attraction. There is some force of attraction between the gas molecules. Okay, so this is and if there is some force of attraction, there is Z value greater than 1 or less than 1. And now if I'll tell you regarding the pressure, first point is force of attraction and then the volume of the gas. Volume of the gas, we are saying that volume of the molecules of gas is almost negligible to the total volume. But no, here the gas particles occupy some spaces. Means if we are going to compress this gas to this mode, this is also occupying some space in the whole container. Okay, so it is also occupying. The correction term due to volume is V minus NB. Means this is somewhat repulsive forces or excluded volume, we can say excluded volume, because suppose this is the whole volume. Okay, whole volume of the container is the volume of the gas, and we are putting these gas molecules in some particular space. This volume is occupied by the molecules of the gas. So this one is the excluded volume and this one is the corrected term, because in the ideal gas we are taking the whole volume as there is no molecule. PV, V is the volume. Okay, now this is the excluded volume. Pressure term, correction term in pressure. We are considering that there is some attractive forces between the gas particles. We have the molecule in the container too and towards the wall too. So in the container there is attractive as well as repulsive forces. Net force is 0 in the container. container. Net force is equal to 0. But near the walls of the container, this molecule is feeling some attractive forces from the inward side, from the inward molecules. So there is some less pressure than the ideal gas, because it is going to strike on the wall of the container. And first we are considering that there is no attractive forces, so it is going to give the whole pressure, like P is equal to pressure force upon area. But now it is attracting by the inward molecules, so pressure that is going to apply on this wall is somewhat less than the previous volume of the ideal gas. We need to consider the attractive forces too for the pressure term. So P plus AN square by V square is the corrected term for the pressure value. Now I am going to move on the real gas equation, that is van der Waals gas equation. 1 minute. Now what is van der Waals gas equation? Van der Waals gas equation is for only real gas. Real gases. Okay, so P plus AN square by V square, V minus NB is equal to nRT if we are considering the number of moles. Okay, tomorrow we are going to discuss regarding the numerical portion of van der Waals gas equation. And some important exceptions related to this concept, because if we are going exceptions related to this equation, because if we are going to change the pressure, means pressure is high or volume is high, somewhat like that, we are going to get a different equation for that one, because H2 and Hg is showing positive deviation. Other gases first show negative deviation, afterwards positive deviation at higher pressure. At higher pressure. So we will meet tomorrow. Thanks for watching.